Hello chemists, and welcome to another in the series of HSC Chemistry and the Industrial Chemistry module. We're going to have a look today at reviewing what we know about equilibrium. Now, equilibrium is a concept that's come up a couple of times in the compulsory units, but it's also something we need to revisit just a little bit when we extend on our understanding of equilibrium for the industrial chemistry component. So a couple of things then to start with. Firstly, the system must be a closed system. So we need to make sure that what we're dealing with is a closed system. We've talked about soft drink bottles, for example. We can have an equilibrium established between the carbon dioxide gas above the liquid and below the lid, and the liquid itself. But once we open the lid, if the lid's unscrewed, the system is open, and equilibrium cannot be achieved in an open system. When we see a system changing by changing color, by being able to measure changes in pressure or volume or electrical conductivity, then we know the system is still reacting. But once these macroscopic properties stop changing, once they become constant, then we have reached a dynamic equilibrium. And of course, the important thing about dynamic equilibrium is that it doesn't mean that the reaction has stopped. It simply means that the rate of the forward reaction is equal to the rate of the reverse reaction. And this is why we distinguish equilibrium systems by the two-headed arrow, indicating that both reactions are occurring simultaneously and hence no macroscopic changes are taking place. So one way of applying our knowledge of equilibrium is just to review the Haber process. Now this is something that we looked at before with 1 mole of nitrogen reacting with 3 moles of hydrogen to produce 2 moles of ammonia. We know that the negative value means this is an exothermic reaction. And as a consequence of that, we can monitor this reaction vessel in terms of pressure. We know that higher pressures will drive the system to the right. In terms of temperature, we know that higher temperatures will actually drive the system to the left, but they will also increase the reaction rates. And so we need some sort of a compromise. In industry, and that's what this topic is all about, we want to make sure that we have maximum yields, minimum time. So we want cost efficiencies. And if we're going to build in cost efficiencies, then we need to make sure that we're getting as much of our product as we can for as limited cost and over as limited an amount of time as possible. And so that's why equilibrium is such an important part of the study of industrial chemistry. So let's have a look then at an example of an equilibrium system. So one example is the manufacture of methanol. Methanol is a two-step process in terms of its manufacture. The first thing we do is we hydrate, or we add water to methane, and that produces two things, carbon monoxide and hydrogen gas. This is an endothermic reaction in the forward direction. And that means that high temperatures will shift this equilibrium to the right. They'll favour the right-hand side. Without having a look at anything at the moment, if I was to ask you what the effect of pressure is, so if I said if we increase pressure, what would be the effect? Well, hopefully you will say, well, there's 1 mole of gas here, 1 mole of gas here, there's 1 mole of gas here, but there's 3 moles of gas here. So there's actually more moles of gas. So pressure favours the side with the lower gas moles, and therefore the equilibrium would shift at a higher pressure back to favouring the reactants. Now, what we can also do is we can use our catalyst to speed up the reaction rate, but don't forget that the catalyst will only speed up the reaction rate. It does not change the equilibrium position. Okay, it will not change the equilibrium position. All it will do is help you reach equilibrium much quicker. And as we've suggested, increased pressure shifts the equilibrium to the left. So therefore, lower pressure is what's needed in this case in order to shift the system to the right. The second half of the methanol production step is this step, and this involves the products of the last reaction, carbon monoxide and hydrogen, reacting to form our final product, which is methanol. This, you'll notice, is an exothermic reaction because it has a negative delta H value. So in this case, what's going to be the consequences as far as pressure is concerned? Well, again, we have 1 mole and 2 moles, so 3 gas moles on the reactant side and only 1 gas mole on the product side. So therefore, for high yield, we want the equilibrium to move to the right, and therefore that is the smaller moles, so therefore we want higher pressure. What about temperature? Well, if it's exothermic, then we have the same dilemma that we have with the Haber process. We want to increase the reaction rate, so we want high temp for increased reaction rate, but low temp favors the forward reaction. Okay, so therefore this is going to be a compromise, some sort of compromise temperature that sits somewhere in the middle. One of the ways of overcoming that is to use a copper catalyst or a zinc catalyst, which allows you to have the temperatures high enough that you're increasing the reaction rate, but not too high that you're having those the equilibrium shifting too far to the left. And that's what we've said in the past. If you're going to maximize your yields, then sometimes you need to compromise on both pressure and temperature. So, to wrap it all up, high reaction rates maintain product formation and economic efficiency, and they are the key goals of industrial chemistry. Low temperatures favour exothermic reactions and high temperatures favour endothermic reactions. But the problem with low temperatures, they also lower the kinetic energy of the individual molecules, and so they can slow the overall reaction rates. And as a consequence, we want to make sure that we're using those compromises. And then any reactants are recycled back through the system in order to make sure that as we increase those concentrations, we continue to shift our equilibrium to the right. Thanks for watching.